Our entire understanding of the vast cosmos depends on how accurately we can measure a single, solitary second. Modern timekeeping relies on the cesium atom. A specific laser frequency strikes the atom, forcing its outer electron to a higher energy level. A single second is exactly the time it takes for 9,192,631,770 of those light waves to pass a point in space. This precision synchronizes our GPS satellites and the internet, but atomic clocks reached a limit. To look deeper into the mechanics of the universe, we need a clock that is shielded from the outside world. Cesium clocks are vulnerable. Stray magnetic fields and heat constantly crash into the outer electrons, distorting their orbits and introducing timekeeping errors. To eliminate this interference, physicists want to move the timekeeping mechanism into the atom's core, the nucleus. In most atoms, the nucleus is a fortress. Protons and neutrons are packed so tightly that changing their energy state requires high-energy, destructive gamma rays rather than precise lasers. Gamma rays are difficult to produce and nearly impossible to control with the stability needed to run a clock. For decades, the idea of a nuclear clock remained a theoretical goal, requiring a specific kind of nucleus that did not seem to exist. That changed with the study of thorium-229, a radioactive isotope that displays a rare physical anomaly. In 1976, researchers at the Idaho National Laboratory were studying uranium-233 waste from Cold War weapons research. They found indirect evidence that its byproduct, thorium-229, possessed a nuclear state that required far less energy to excite than any other known isotope. Every nucleus balances two massive forces. Electromagnetism pushes positively charged protons apart, while the strong nuclear force binds them together. In thorium-229, these forces rest in delicate equilibrium. When its outermost neutron flips its spin, both forces change, but cancel each other out almost perfectly. This cancellation reduces the energy needed to excite the nucleus by a factor of 10,000. Because this energy requirement is so low, thorium-229 is the only nucleus that can be controlled by a precise ultraviolet laser. Finding the exact frequency was a decades-long search. Physicists knew the low energy state existed, but they had to test thousands of potential laser wavelengths to find the one that would trigger it. Researchers embedded thorium-229 inside solid crystals, allowing them to hit quadrillions of atoms at once and rapidly rule out incorrect frequencies. In 2023, a team at CERN detected the faint ultraviolet light emitted by the thorium nucleus as it decayed. This measurement narrowed the search field, giving laser hunters a specific target. The marathon search finally ended in May 2024 at Gila in Boulder, Colorado. A team successfully tuned an ultraviolet laser to the exact frequency needed to excite the thorium-229 nucleus, achieving a measurement millions of times more precise than previous efforts. This 3:42 a.m. discovery transformed thorium-229 from a nuclear mystery into a working clock. While it functions as a timepiece, the nuclear clock's primary role is measuring the stability of the forces that govern the universe. Many theories in modern physics, including string theory and models for dark matter, predict that the fundamental constants of nature, like the speed of light, are not actually constant. They may be slowly shifting over time. The thorium-229 clock is designed to detect these shifts. Because the clock's frequency depends on the cancellation of massive internal forces, any change in the strength of those forces will disrupt the balance and change the light the nucleus emits. Physicists can now use this tool to look for variations in these constants down to 1 part in 10 trillion. By isolating the timekeeping mechanism inside the nucleus, scientists have created a sensor that is shielded from local interference and sensitive only to the universe itself. This Cold War byproduct has become a cosmic antenna, capable of proving whether the laws of physics are as immutable as they appear.